Hi. Hi, y'all. Back for another round of physics, I see. And we'll keep our discussion going about potential energy here. So, in the last video, we talked about both the origins of the potential energy and a rough idea on how to actually calculate it. And just as a reminder, I say the origin, from where does the potential energy arise? And the idea is that it really is a byproduct of the choice of system versus the surroundings. Rounding. Okay. If we make the appropriate choice of system, then we'll have, for example, kinetic energies or potential energies to consider. Whereas if we make an alternative choice of the system, and then we'll have things in the surroundings that do work on our system. Okay? So it really comes down to what choice of system versus surrounding you make. And yeah, there's some more discussion about, okay, well, it depends on not the consideration of the center of mass, but you have to think about more physically, where does it arise from? It comes from the orientation of the different pieces of your system. So a different way to say it is the potential energy is associated with how your system is arranged. So if your rubber band is stretched, that changes the arrangement of your system, and there's some energy stored in there. Okay. So that's where I say system and surrounding. And to go further, it kind of gave you an idea about how to actually calculate some of these potential energies. If you recall correctly, or if you recall, at one point for the spring potential energy, we had something like the change in potential energy for a spring was given by 1/2 kx squared. And this is assuming that the initial stretch length is 0. Okay. If you wanted to get further, if we wanted to get the more general, we should say something like 1/2 kx final squared minus x naught squared. Something like that. Okay. And this would be as if not starting from equilibrium. If not starting from equilibrium. In other words, you're not starting from the natural length of the spring. And if you don't remember how we actually came up with this, I'd say go back and watch the entire video. But the shortcut version is we found the work done by the spring, which was negative 1/2 kx squared. And then we asked ourselves, if we include the spring into our system, we basically found that this would be the amount of energy that the kinetic energy changes by. So we found, hey, if we include the spring in our system, the change in kinetic energy is 1/2 kx squared. And therefore, our change in our spring potential must equal 1/2 kx squared, using the idea of energy being zero sum. So energy is zero sum. If our kinetic energy decreased, then our potential energy must have increased. So that's the brief outline of what the last video was. And again, so important that I basically repeated myself twice. So let's get at it. The question then becomes, what other potential energies can we calculate? What other potential energies are there? So we'll say, what others use? Question mark. Okay. And we'll develop a couple of them. So the first one we'll do the gravitational potential energy. Gravitational potential energy. And I'll say near Earth. Near Earth. So consider, for example, a ball, and we just drop it. We can go through the whole same song and dance. Okay. We could say, for example, let's put the system as the ball. We'll do the surroundings as the Earth. Okay. We'll have our initial state just dropped. We'll do our final state as just before hitting ground. And we can run our problem. Since we have our system as our ball, we'll approximate it as a point particle, and we'll apply our work kinetic energy theorem. So we get our work is equal to our change in kinetic energy. Well, free body diagram of the ball. Here's the ball. Here's the only force acting on it. Fg. And the displacement of the ball is also in that direction. Delta R. So we'll go ahead and plug in the definition for the work here. And I'll use it as the summation for right now, just to remind ourselves that, hey, this technically has multiple pieces to it if the force is mean. So I'll leave it like this, Ke. But in this case, let's see, we'll call positive x or positive y up. In this case, we have our definition of our force. Our net force is simply the force of gravity, so I'll put in mg. Okay. Our displacement is just the change in height, so I'll just put h here. Okay. And we have negative y hat dotted into negative y hat. And this will equal Ke. Okay. Now we'll go ahead. Y hat dot y hat is just 1. And so we get something that says mgh is equal to our change in the kinetic energy. Okay. I'll go ahead and move that. There we go. Cool. So we have this. Let's go ahead and see what happens if we do it the other way, namely, oops, excuse me. If we do it the other way, namely, let's go ahead and put our system as the ball and ball and Earth. Of course, bat has one T. And that means that there's nothing in our surroundings. I'll put Na here. Nothing. Good. Well, now that we go through and we say, well, wait a minute, if there's nothing in our surroundings, we'll use the same initial and final states from last time. And we go to our relationship from the first law of thermodynamics, the more general relationship. We have 0 over here equals a change in kinetic energy plus the change in gravitational potential energy. Of course, if I move the kinetic energy, rearrange this, I get Ke is equal to negative delta Ug. And now I'm at the situation where I have 2 equations. Let me go ahead right here and here. Let's just go ahead and sub. And so I get something that says the change in gravitational potential energy is given as mgh with the negative sign. Cool. Or if you wanted to, in more general, we'd say our change in gravitational potential energy is equal to mg, and I'll put delta y here. Delta y. So this would be the gravitational potential energy close to the surface of the Earth. Mg delta y, or mgh if you will. Probably sounds familiar anyway. Good? Okay. Well, we might as well keep going. So you've got for the spring you've got close to Earth. Why don't I give you, we'll do the last one, I'll give you the full-blown, let's say the gravitational potential energy for any situation. Okay? In other words, rather than little g, close near Earth, let's go ahead and do it for big G. And I'll say any case. Okay. Very good. We'll get a little bit more calculus in here. Let's go ahead and we'll say, let's say I have a ball and I'm dropping it towards a planet. Okay. So the work, and I'll say this is my system. Here's my surroundings, SURR. Okay. So here we'd have to do something. We'll have to use the full-blown definition since we're dealing with a mean force. And I'll do our gravitational force. I'll do big G here, dotted into our infinitesimal displacements, our little delta r's as the whole thing falls. So each of these little paths, these little displacements, I'll call those delta r's. And we have to take the sum of all of them as the ball falls down. Well, we'll call this the y direction. Just call that positive way towards the center of the planet. And I need to substitute in the expression for the gravitational force. So I've got G, mass of the ball, mass of the planet, P, over r squared, dr. We notice that the gravitational force is towards the center, and that's also the direction of the displacement. So the dot product, I'll say our dot product in this case will give us r hat dot r hat, and this will give us 1. Right? The displacement is in the same direction as the gravitational force. I'll go ahead, integrate. Now, again, the question then becomes, these are all constants, G, M, B, M, P. I'll pull those out just for simplicity. B, M, P. And again, the question becomes the derivative, I'll call it ddr this time, of what function f of r gives me 1 over r squared. So I'm looking for what function, when I take a derivative, gives me 1 over r squared. You got it? Good. Hopefully you see, and this is always, you can guess and check, right? That's fine. Guess and check. You say, well, what is it ln? How about ln of r? Ln of r. If you take a derivative of ln of r, you get close 1 over r, right? So that's not it. Well, how about if I do a power, if I do r squared? Well, that's not going to work either. That would give me 2r. My r's in the numerator, not the denominator. But hopefully you hit on, oh, wait a minute, I know what this is. This is d dr of r to the negative 1. And I'll put a negative sign in there. So if I apply my power rule, I take my negative 1, I put it in front. So negative 1 times 1 is, negative 1 times negative 1 is 1. And I decrease my power by 1. I get negative 2. So evidently, when I do this, and remember, that's what the integral does. It's trying to find the function that when you take a derivative, it equals whatever's in what we call the integrand. Okay, so right here, this 1 over r squared. So we find out G MB MP divided by r. Put the negative sign in there. That is the work done by the planet, the surroundings, to move the ball, or as the ball falls. And you notice, it should be positive work. Oh, excuse me. Oh, terrible, terrible, terrible. I'm so sorry. Don't forget we got a negative sign in here. There we go. Right? So it does positive work on it. Yeah. Okay. Oops, sorry about that. Okay, so now we have an expression for our work. Evidently, that must mean that if I decide to take the planet and move it into my my system, evidently that would mean that my gravitational potential energy is given by gm ball mp over r with the negative sign. Cool. You guys don't seem impressed. It's pretty cool, huh? So let's go ahead. I'll give you all three of these. So now we have at least three. We have the change in potential energy of a spring is given by 1/2 k, I'll say x final squared minus x naught squared. Okay. We have the change in gravitational potential energy close to Earth is just given by mg delta y. Okay. And you have the change in gravitational potential energy when you're talking about any kind of planet. That would be g m1 m2 over r. I'll put a negative sign in there. Okay. Of course, I guess maybe I should, excuse me, I'll do this a little bit. Maybe I shouldn't do it quite like that. I'll say, hey, let's do it like this. Say the change in gravitational potential energy is g m1 m2, don't forget the negative sign, and I'll say 1 over r final minus 1 over r initial. Okay, so it looks a little bit different there. Okay. And here, this is three potential energies that we can now use. And remember, this is if I put the spring in my system, or if I put the Earth in my system, or I put some unknown planet in my system. Okay. Now, the other piece that I guess I'll point out to you here, it's not by accident. You say, well, gee, Greg, these look an awful lot like the forces. And if you remember how we actually got these in the first place, we essentially were setting the work equal to the negative change in potential energy. Of course, work is defined as F dot dr equals, I'll say this, let me rewrite this. I'll say it's negative du. Okay. Now, integrals and derivatives undo each other. So if I take a derivative of this side, I'll say ddr. I should do the same thing over here, dr. That undoes, this derivative undoes that integral. And so this is written as f equals negative du dr. In other words, if I want to know the force associated with, for example, the gravitational potential energy, all I have to do is take a derivative. Okay? So that just gives you another kind of way to latch onto it. It's not by accident that the gravitational force, which is g m1 m2 over r squared, get a negative sign in there, r hat. It's not by accident that that looks a lot like g m1 m2 over r squared. Oh, excuse me, muscle memory. It's not by accident that those two look awfully similar. And you'll see that Hooke's law, spring force, kx. Okay. Gravitational, or excuse me, the potential energy, 1/2 kx squared. You can see I take a derivative of this, that gives me this. Okay. So I usually don't have all of these equations memorized. I usually have for example, the energy ones, and then I know taking derivatives give me the forces. I guess I should probably put little vectors on there as well. Okay. So that's just a little hint. Now, this relationship does not always hold. Okay. This relationship is only useful for what are called conservative forces. So let me go ahead. This relationship is only useful for what's called conservative forces. Oops, excuse me. X to forces only. What does that mean? Conservative forces are forces that only depend on the initial and the final states. Or maybe a different way to say it, excuse me, this is a better way of saying it. Conservative forces are path independent. Path independent. Okay. In other words, the amount of energy stored, okay, the amount of potential energy does not depend on it does not depend on the path taken to get from the initial to the final states. An example of this, for example, say that you start on sea level and you walk to the top of, I don't know, Mount McKinley. I guess it's not Mount McKinley anymore, but we'll say Mount McKinley. Okay? It does not matter if you start at sea level and you walk, I don't know, to Canada, and then you walk up the Rockies and then back down to sea level, and maybe you go over to Death Valley, and then you finally walk up to the top of Mount McKinley. Okay? The only thing that matters is where you started at sea level, and at the top of Mount McKinley. Okay? This and this are the only two spots that matter. It doesn't matter if you walked up some mountains in the interlude. You go up some mountains and then come back down and go up more. Maybe you walk around Mount McKinley a couple times and then get to the top. Okay? All of that doesn't matter. The only thing that matters is the starting spot and the ending spot. Okay? That would be a conservative force. Okay? Same thing with the spring. Say you stretch it a lot, and then you stretch it a lot more, and then maybe 3/4 stretch, and then you stretch it back up to the full stretch. Okay? So the issue there is that, okay, well, again, it doesn't matter what happens in between. The only thing that matters for calculating the final potential energy is the initial and the final. Okay? What's a different one that does non-conservative? Let me give you an example of a non-conservative. The frictional force is a non-conservative force. Okay. Say, for example, in one situation, you have a box sliding on a floor to another location. Okay, just directly, slides directly. And in another case, say you have the box slide one way and that slides back, and then it does some sort of back and forth sliding. It slides one way and it slides the other way, slides the other way again. In these two situations, you'll see that this one has a different energy loss than that one because they took two different paths. Even though they start at the same spot and they end at the same spot, the fact that they had to take two different paths means that they're going to lose different amounts of energy. And that means that this is a non-conservative force. Okay? So this relationship between the potential energy, the change in the potential energy, and the force only holds for conservative forces. Okay? Path independent. Fortunately, a lot of the ones that are really cool, the ones that are fun to play with, gravity, springs, those are path independent. You're good to go. Some of the more difficult ones, frictional force, air drag. So I'll say air drag. If I can spell drag, air drag, non-conservative. These are a no-go. Okay? That's why you won't see an expression for the potential energy of the Air Force. That sounds weird. Okay, well, you know what I mean. Any case, I'll leave it there for right now. Next video, we'll run some practice problems. Thanks for your attention. I'll see you next time.